شكرا.
Hello, everybody. I,
وعليكم.
I want I want to thank you all for giving me the chance to be part of this ceremony. Uh, First of all, I want to introduce myself. I'm Diaa, process engineer at MD, UAE, branch. My master thesis is about mathematical modeling for spiral wound membrane separation for CO2 from the natural gas. The topics that we want to discuss in this presentation is, first of all, introduction to CO2 removal and spiral wound membranes, theoretical framework for our baseline in this thesis, model basis on assumption, the model itself and its implementation. And finally, we will discuss a case study based on the Egyptian natural gas field. At the beginning, uh, uh, CO2 removal from natural gas is not just a technical requirement. It's an economic and environmental necessity because CO2 removal is essential for meeting the pipeline specification, especially to avoid the excessive dry ice formation through the gas pipeline. So we have to make CO2 concentration below 2 to 3%. Also, in the presence of hydration through process equipment, this environment can cause carbonic acid with CO2, even if the reaction is not with high kinetics, but the carbonic acid is highly corrosive. The presence of CO2 in the natural gas decreases its heating value, so it's essential to eliminate the CO2 from the natural gas stream. Spiral wound membranes offer a compelling alternative because when it is compared to the ordinary amine absorption process, the amine absorption process acquires a lot of energy, maybe 4 to 6 gigajoule per ton of CO2 removed. When it is compared to the membrane separation, this value is diminished to around 60 to 70 of the energy required. Also, the compact footprint of the module of the membrane makes it worth it for the process industry. Finally, there is no chemicals or moving part in the membrane, so it has a low hazard identification when it is compared to amine absorption. Regarding a theoretical part, gas transport through dense polymer membrane follow the solution diffusion mechanism, a three-step process that governs selective separation. First, gas molecules diffuses or dissolve into the polymer matrix as a high pressure interface, which is called sorption. This process is controlled through the Henry law or Landmeyer model, or the combination of both. Then the diffusion through the membrane surface itself, which is controlled by Fick's law, which represents a first order differential equation between the concentration difference at the two surfaces of the membrane side and the thickness of membrane. Third part is desorption at the low pressure side. The main parameters that is essential in the modeling of the membrane is the difference in solubility and the diffusivity, and the multiplication of force gives us the term permeability. The permeability identify the rate at which substance can permeate or move through the membrane from the at its two sides. Then we have the other parameter, which is called the selectivity, which is the ratio between the permeability of substance A and substance B. The permeability is affected by the solubility and diffusivity. Diffusivity is controlled by the term of temperature alone, based on Arrhenius equation. As the temperature increases, the diffusivity also increases. But the term solubility, on the other hand, is controlled by the pressure. As the pressure increases, the solubility increases. We will discuss it. We'll discuss these factors at the end of our presentation. The core model assumption. Our model represents a steady state operation, isothermal conditions. The temperature will not be changed. Ideal gas behavior. We consider that the gas movements through the axial direction, but the separation along the membrane surface through the radial direction. Well, the solution diffusion mechanism governs all the gas transport with no convective flow through the venous membrane. We account for concentration polarization at the membrane surface, where local CO2 depletion produces the effective driving force. And this is a pioneer introduction for our model, because the previous models couldn't take in the consideration the concentration polarization and its calculations. The pressure dependence, permeability coefficients capture the non-ideal behavior observed in real membranes at elevated pressures. This is particularly important for CO2, which shows significant pressure dependence due to plasticization effects. Actually, we are not counting the plasticization, but we counting the concentration polarization. Permeation flux through the membrane. Permeation flux through the membrane represents the amount of the gas that we want to eliminate from the mainstream. And as we said before, this flux is calculated based on fixed law. And the final form we count in our model is the flux rate equals to the permeability of each substance divided by the thickness of the membrane multiplied by the partial pressure of the substance at the feed side multiplied by the concentration polarization factor minus the partial pressure at the permeate side. Then we have the mass balance equation, which is applied from the general mass balance equations that the feed gas minus the output equal to the permeation flux. So this equation is diminished to the derivation of the concentration of each substance at the permeate side multiplied by the velocity at the permeate side by the radius, by the deviation in radius of the membrane equals to the permeation flux. The other equation or the last equation that we are considering in our model is the pressure drop calculation through the model, which is represented by Dorsey law. The pressure drop equals to negative the viscosity multiplied by the velocity. Uh, the, sorry. The model implementation flow chart, we have input, processing, and output. The input for the model is composition, flow rate, temperature, and pressure, membrane properties, and operating parameters like the pressure ratio between the inlet side and permeate side. The processing is solving all the equation discussed at the previous slide through numerical equations. And the output is a CO2 removal efficiency, methane recovery, and Egyptian gas, CO2 removal efficiency and methane recovery. Um, One of the important parts that we want to discuss is the critical parameters we have in this model, which is a pressure ratio between the inlet side and the permeate. We have found that the ratio the ratio must be 2 to 0.8. This is the optimum ratio, and the feed flow rate, as the feed flow rate increases, the methane recovery increases, and the CO2 removal decreases. The membrane thickness, as the membrane thickness increases, the methane recovery increases, and the CO2 recovery decreases. The membrane area, we have found from our trials on the models that the optimum area for one stage membrane separation is 200 meters square. The model was tested against three main fields in Egypt, and we found that the results is approximately with percentage error that is less than 9%, which is approved by my doctors. The model advantage is parametric sensitivity, confines influence of each parameter with sensitivity coefficient for optimization, computational efficiency, a successor of a state method, which is a numerical method to solve a number of differential equation, has a rapid conversion and solution. Field validation, we have validated our model against a number of fields in Egypt, and it gives us a great results. Operational flexibility, multi-component capability, modular architecture. Our key finding is that the pressure ratio is the most influencing parameter. Sensitivity is 0.85, and that means that the pressure ratio should be in the range of 2 to 2.85. Optimal membrane thickness is 1 to 2 micrometer. Membrane area shows diminishing returns beyond 200 square meter. Future directions, we are now going to indicate the multi-stage membrane separation. In the future, we'll consider the economic optimization, investigate advanced membrane materials instead of using the spiral wound. develop real-time control because this model is a steady state. We don't have any transient consideration. Finally, this research was supported by the Chemical Engineering Department, Faculty of Engineering, Alexandria University. I'm grateful for you all and for my doctors. And thank you all. I'm ready for any question.